Welcome everybody to another night sky news with me, astrophysicist Dr. Becky Smethurst. What a month it has been for both astronomy research and for stargazing. So without any further ado, let's just dive right into this. All right, let's start with the thing that everybody has been talking about, and that is Comet NEOWISE. So over there, so we've not been able to spot it here yet. Little did she know that she'd spot it that very same night. Hey everybody, Editing Becky just jumping in here quickly. Now I filmed all of this footage before I'd even been able to see the comet myself, but that very night it was clear enough I managed to go out and find it. I got a little bit overexcited on social media about it, but it was my very first comet, so I was on such a high. Anyway, if you want to spot it yourself, here's what you need to do. You need to find the Plough, Big Dipper, Ursa Major, whatever you call it, and you need to sort of go down towards the horizon from there, and then either sort of slightly right or slightly left, depending, first of all, where you are in the world, and also depending when in July you're actually trying to spot this. So what I'm going to do is I'm going to put a link in the description that you can put in your specific location and then a specific day and time, and then it will show you where the comet is in relation to the Plough or the Big Dipper. Now, I managed to be able to spot it here in the south of the UK at around about half midnight. And I could actually see it with my naked eye as well, despite the fact that in the exact same direction was just this giant bright street lamp as well. To the naked eye, it looks like a sort of fuzzy star with a fuzzy smudge above it. Now, my eyesight is pretty good. And okay, yeah, I was in the suburbs, but I still did have quite a bit of light pollution around. It will depend on your sky conditions, like your humidity, your altitude, you know, how clear it is, how the light pollution is around you, and also how good your eyesight is, whether you'll be able to see it with the naked eye. I managed to be able to confirm that what I was looking at was actually the comet just using my phone. So I used a normal, just 3-second night mode shot with my iPhone 11, just pointed it roughly in the right direction towards the Plough to confirm, oh yeah, that fuzzy smudge thing is actually Comet NEOWISE. Now, if you have binoculars, that's another way you could confirm that what you think is that fuzzy patch in the sky is actually Comet NEOWISE, and it will probably make it look even more spectacular. I haven't seen it through binoculars yet because somehow we don't have any here in the house, but I've got a family member coming at the weekend that, fingers crossed, is going to bring down some binoculars. So I'll share on my social media my reaction to seeing it through binoculars and how it compares to sort of naked eye and with your phone. But for now, here's what I got with a 30-second exposure on my iPhone 11, just propped up outside on the garden table. You can spot the Plough in the top left there as well. For comparison, here's what one of my subscribers, Adam Spink, captured with his Google Pixel 3, which had a 58mm lens from Moment attached to it as well. It's really lovely to see, so thanks for sending that in, Adam. We also broke out our chunky DSLR here as well, which is a Nikon with a 35mm lens, and we managed to snap these beauties literally with it on a tripod, precariously balanced, pointing out of the spare bedroom window. I might play around with trying to stack some of the images we took this week, so look out for those again on my social media. It is set to get brighter as it gets closer to Earth. Its closest pass is going to be on Wednesday the 22nd of July, which is the day this video comes out. So fingers crossed for clear skies for everybody. All right, back to filming, Becky. So as a reminder, a comet is a rocky, icy body in the solar system that orbits the sun. But instead of on sort of a roughly round, but ever so slightly oval shape, like what the Earth's orbit is, this is on a really elongated oval shape. So it'll go really far away from the sun into sort of the far reaches of the solar system and sort of get incredibly cold and freeze out as it does. And then when it gets back towards the sun, all of the ice that's frozen out in the far reaches will start to melt. That releases, you know, gas and dust from the inside of the comet that then sort of evaporates and forms this very thin atmosphere around the comet. Radiation from the sun then impacts on that thin atmosphere and sends it streaming away from the sun in a very long tail, which is what makes it look so spectacular to us from Earth. Now, the other two comets this year that people had high hopes that they would become very visible in the night sky too, as were Comet Atlas and Comet Swan. They actually broke up as they got too close to the sun. With all of that sort of melting and outgassing, it can sometimes break up comets. And so people were quite disappointed when that happened, but NEOWISE has swooped in to save the day. Or save the year at this point, because the universe knows we need something good to come out of 2020. Now, all of that dust and gas debris left behind by a comet as it orbits the sun is what causes meteor showers when the Earth passes through that sort of debris trail that the comet leaves behind. And it just so happens that we'll be passing the debris trail of two of the comets whilst Comet NEOWISE is going to be visible in the sky. And so that's going to cause two very popular meteor showers, the Delta Aquarids meteor shower at the end of July, and then the Perseids meteor shower mid-August time. Now the Perseids meteor shower is just hands down the best meteor shower of the year. There's something like 60 meteors per hour during its peak, which this year is going to be 12th of August. Now the Delta Aquarids are probably more like 15 to 20 meteors per hour, so not quite as spectacular as the Perseids, but the Delta Aquarids really are going to be more for the southern hemisphere, where the Perseids is really going to be for the northern hemisphere. Now wherever you are in the world, sort of in late July, if you do see a meteor, it's much more likely that it's come from Delta Aquarids than the Perseids, because the Delta Aquarids you really can see from wherever you are on the globe. It's just southern hemisphere, you're much more likely to spot them. For those in the northern hemisphere, Perseid should put on a great show. The only problem is that the moon is still up during the peak of the meteor shower on the 12th of August. So it's probably going to be best just after that, when there'll be slightly less meteors per hour, but you're not contending with the moon. So you're much more likely to spot more of them because you'll see the fainter ones and not just the brighter ones that weren't, blown out by the light of the moon. To spot the Perseids, you need to find Cassiopeia, or the W, another very famous constellation, and basically look anywhere else in the sky but that, and then you should be able to spot the meteors which appear to streak away from the area of the sky near Cassiopeia. All right, let's switch gears now from stargazing or comet or meteor gazing this month, and let's talk about all the space news that's been happening. Now, I don't know if anybody else noticed this month, but there was so many space-related news stories that came out in the past couple of weeks, and I ended up with a list of 9 stories to cover, which is just absolutely crazy. So to save my own scientific research from just getting snowed under by video editing next week, what I'm going to do is actually talk about some of the stories over on my Instagram account. So if you want to know more about the possible giant star spots on Betelgeuse that could explain its strange dimming from last year, and this white dwarf that might have been ejected from a failed supernova explosion, then head over to my Instagram. I'll put them on stories just as this video goes live as well, and then I'll save them in a highlight if you're watching it later down the line. But if you're interested in those, go over and check out my Instagram for that. So continuing the tradition of starting this news segment with just something pretty to look at, have you guys seen this incredible video that was released by NASA's Solar Dynamics Observatory? So as of June 2020, the SDO has been taking a picture of the sun every 3/4 of a second for a decade. That's 425 million high-resolution images of the sun, or 20 million gigabytes of data over the past 10 years. So they released a time-lapse of that data, compressing 10 years down into a single hour. It's just incredible to look at how the sun not only changes on a day-to-day basis, but also on a yearly basis as well. Now, there's going to be a lot more images and results being released about the sun in the next coming years, because we've got NASA's Parker Solar Probe and ESA's Solar Orbiter both on their way to orbit and study the sun in great detail. So unlike the Solar Dynamics Observatory, which is about half the distance between the Earth and the sun is where it orbits, these are going to be within the orbit of Mercury at their closest approaches. So they're going to be able to see the sun in great detail. So actually the very first pictures from ESA's Solar Orbiter were released this month, and they showed the surface of the sun in unlike any detail that anyone has seen before. And what they revealed was these structures on the surface that we'd never seen before, these tiny little sort of almost like solar flares, the sort of massive ones that we see from Earth that, end up causing our aurora, but like in miniature version. They've been dubbed sort of like campfires by the Solar Orbiter team, which is an analogy that I love. What's great though about these little miniature solar flare campfire things is that they could possibly be an explanation for why the sun's corona, its very, very sort of thin atmosphere that extends a lot further than sort of what you would class as sort of almost the surface of the sun, is way, way hotter than the actual surface. They could sort of be the reason why that corona has been heated to such high temperatures. That's sort of the maybe tentative hypothesis at the minute, though. They're going to be working on that in the next coming years. And so when there is anything more concrete, I'll let you know on this channel. So the next big piece of news that we need to talk about is that the LIGO and Virgo collaboration teams detected gravitational waves from the merger of two objects. One of those objects was a 23-ish times the mass of the sun black hole. The other object was something else. That something else was an object that was 2.6 times the mass of the sun. That means that it is either the heaviest neutron star ever detected or the lightest black hole ever detected. The previous record holders for that, the heaviest neutron star, was 2.5 times the mass of the sun, which we've talked about on a previous Night Sky News video on this channel. The lightest black hole ever discovered or known of before was 5 times the mass of the sun. And so that difference sort of from the 2.5 times the mass of the sun and the 5 times the mass of the sun going from neutron star to black hole has been called the very original mass gap. And it's one of those things that we can't really explain. So I always like to describe a neutron star as like the Pikachu to a black hole's Raichu, right? If you keep adding more and more and more mass to a neutron star, it will evolve because the force exerted by gravity that's pushing on those neutrons that are already as tightly packed as they can go becomes too much and the whole thing collapses down into a black hole. Now, the point though at which that happens is not very well understood.
Oh, jeez.
Previous models put it at about 2.16 times the mass of the sun, but then they found that 2.5 times the mass of the sun neutron star not long ago. So then the models were revised based on that new observation, and they came up with a new number of 2.6 times the mass of the sun, which is the mass of the object they found here. Now, other neutron star mergers that LIGO and Virgo have detected have also given off a flash of light, of electromagnetic waves at the same time that we've been able to detect with telescopes on Earth. This one didn't. And there could be a couple of reasons for why it didn't. The first one being that it was two black holes, and it was the smallest black hole at 2.6 times the mass of the sun that's merged with the normal one that LIGO and Virgo tend to find at 23 times the mass of the sun. That could be one hypothesis. If it's a neutron star, though, then you could explain the lack of light just from the fact that it is actually 6 times further away than the other sources that they've detected, and therefore the light from it might be much fainter, and so we've just not detected it. Or that the black hole sort of swallowed the neutron star whole, and therefore that's why you haven't got any light from it. And we don't know which of those sort of 3 hypotheses is right yet, which is why sort of people are referring to this as, the merger of a black hole with something else, like another object that could be a black hole or could be a neutron star. The hope is that LIGO and Virgo will continue to detect mergers just like this of things right on that mass limit, and that should give us a much better idea of what is going on in terms of like statistics and population, whether, some give off flashes, some don't, and maybe we can work something out from that. So I guess it's just a waiting game while we wait for LIGO and Virgo to maybe detect more of these, but when they do, you'll find out right here. So sticking on this topic of black holes, the typical way that a black hole is made is through a supernova. So when a star, maybe 20 times the mass of the sun or more, runs out of hydrogen fuel to burn in the place where it's actually hot enough for nuclear fusion to happen in the core, and then what happens is that those outer layers then collapse inwards, they rebound and get thrown back out into space in this huge sort of explosion, whereas the central core will then collapse down into a black hole that's somewhere in this sort of mass gap range of like 2.5 to 5-ish times the mass of the sun. If your star isn't big enough, to give you a black hole. If it's not 20 times the mass of the sun or more, then you're probably going to get a neutron star. And if it's something like the sun, you'll get a white dwarf instead. I guess sticking to the Pokemon analogy, a white dwarf would be a Pichu. Now that's the typical way we think black holes are formed, but astronomers this month have found evidence of a massive star that has just completely disappeared, perhaps skipping the supernova entirely and just directly collapsing all of it down into a black hole. This work was from Allen and collaborators, who found that in the total light output by the little dwarf galaxy they were studying, the signatures of the most massive luminous star had disappeared. And those signatures were very easy to spot because it really did dominate the light, this star. It was outgassing, it was very variable, it wasn't a very stable star. So the disappearance of those signatures could mean one of two things, right? Either the star has got its life together, it's no longer unstable and variable, and it's sort of settled back down so that it's no longer dominating the light of that dwarf galaxy. Other thing that could have happened is that it was reaching the end of its life, hence why it was so unstable and variable, but somehow it skipped the supernova process entirely and the whole thing collapsed down into a black hole. That might sound quite far-fetched, but we have actually seen something like that happen before. Back in 2015, astronomers found a star in our own galaxy that just completely disappeared. It was there in one image and not there in the next. So that discovery back in 2015 lends a lot of support to this hypothesis that this star could also have done the same thing, directly collapsed into a black hole. What amazes me is that in such a short space of time, we've found two candidate stars that could have done this. 5 years, astronomically speaking, is nothing, right? Which might suggest that that process of a star collapsing down into a black hole at the end of its life is maybe not as rare as we first thought. And there is possibly a way of making a black hole that is actually 20, 30 times the mass of the sun directly from a star, rather than making something from just the core of the star that's maybe 3 times the mass of the sun. And maybe that would explain, the black holes that LIGO and Virgo have been detecting on average that are around about that sort of 20 to 40 times the mass of the sun range. It's very interesting. It feels like all of the pieces are falling into place, but obviously 2 data points does not make a trend. And so again, it's a waiting game to see if we can maybe spot any more of these stars sort of winking out of existence, either in our own galaxy using images or by studying the signatures of light from other galaxies that are dominated by these very variable, massive, very luminous stars. I think it's a really exciting sort of avenue of research, and I'm really looking forward to seeing what comes out of it. Now, finally, I want to end on something really cool that's been announced today while I'm filming. So I've not quite had a chance to sort of digest everything yet, but it's a result that is going to play into this so-called crisis in cosmology. Now, I covered this back in December's Night Sky News, and if you haven't seen that video, I would maybe go back and watch it just to understand everything I'm about to say. So today, the largest 3D map of the universe ever created has been released, along with 20 journal articles describing all the work that's been done on it, which total 500 pages. Hence why I haven't been able to digest everything properly yet. So the collaboration that's done this is the EBOS team from the Sloan Digital Sky Survey, which is a telescope that essentially just surveys the sky every single night and records the position of basically every object that it sees. Now, the EBOS team have done is add to what's been previously done by that telescope over the past 20 years. And in these 20 new papers, they described how they targeted 2 million galaxies and quasars over 11 billion years of the universe's history. So they've looked back 11 billion light years. And so we see what the universe looked like all the way back when it was only, say, 3 billion light years old. Such a detailed map over such a large chunk of time, it's 80% of the universe's history, allows you to track the universe's expansion. From this, they've been able to pinpoint the exact moment that the universe's expansion started accelerating, which was 6 billion years ago, caused by this unknown energy or force that we've dubbed dark energy. It's obviously when it started to dominate the universe is 6 billion years ago. Now, this is where this starts to play into this crisis in cosmology, because if you have the rate of expansion, then you can also get the age of the universe. And if you've seen that previous video, you will know that lots of different methods for measuring the rate of expansion in the age of the universe give us different answers. And the things where we measure locally from, say, supernova in distant galaxies compared to when we measure it on a universal scale across the entire universe using the echo from the Big Bang, the light sort of relic from the Big Bang, the cosmic microwave background, they give two very different results. So much now that the errors on those answers are also not overlapping either. So there's sort of definitely two different camps that they've fallen into. And so it's very interesting to see now what the eBOS's collaboration's measurement of this will be. And so for my first look at this today, the rate of expansion and therefore the age of the universe that they're deriving is actually much more in agreement with the universal way of measuring this with, say, the cosmic microwave background, this echo of the Big Bang. Which is very interesting because the Crisis in Cosmology sort of video discussed this as that maybe the difference in these two camps is because there's a bias in either the data of the cosmic microwave background or the way that we've been analysing it, or maybe there's some systematic error that we're just not aware of. But the fact that this result, which covers both the local and global scales, is agreeing with the cosmic microwave background suggests there might be some sort of unknown bias in the local measurements instead. The other thing that this result is showing is that the universe is very likely flat. They were talking about the geometry of the universe here, so not necessarily the curvature of space by like general relativity, and we're not talking about like the shape of the universe, i.e. like the overall topology of it. We're talking about the geometry of space-time itself. Like, is space-time flat, i.e. like would two parallel lines never meet, or is space-time curved and therefore they would meet, or is space-time curved the other way, in which case they would never meet? And the Crisis in Cosmology paper that came out in December suggested maybe we could solve our problems in cosmology if the universe isn't flat, but that sort of threw everything off. So it's interesting to see that we can actually reconcile sort of these two things not matching, even with a flat universe, and saying actually no, the cosmic microwave background data and this sort of map of the structure of the universe are maybe starting to agree. I know it's a lot to take in. It's the age of the universe. It's the rate of expansion of the universe. It's a big 3D map of the universe. It's pinpointing when dark energy first started to dominate. It's okay to feel a little bit overwhelmed at the minute. I know I do. I'm still excited to jump into the sort of 20 odd papers that they've published as well today, you know, to really hear from the scientists themselves what they think are the big sort of scientific consequences of all this data and these results. So if I find anything when I do that, I will report back next month. Until then though, hope I haven't fried your brain too much with all this information, and until then, happy comet hunting, everybody. Which meant that it was either the lightest neutron star ever detected or the wrong way round. The heaviest black hole known before. Why? I just want to say that black holes are heavy, I guess. We talked about in a previous Night Sky News video at some point, the lightest black hole ever discovered. Why? Which means that it is either the lightest neutron. Jesus Christ, Becky. My life is going fine now, LIGO's in it. I look into your eyes and I see the gravitational waves. Now that's the typical way we think black holes are formed, but as excuse me. I keep trying to do this outro, but my battery's dying and my stomach keeps rumbling and interrupting all my takes.